So our first speaker today is going to be virtual. We have Duncan Rayner on the line, and he's going to present to us Prioritising Restoration on New South Wales Coastal Floodplains. Hi Rayner, I'm Valerie Hager. I'm going to chair this session as well, so I'll hand it over.
Thanks so much, Valerie. Good morning, everyone. Thanks for having me today. I hope you can hear me loud and clear and see my video stream of the presentation. So today I'm going to be talking about prioritising restoration on New South Wales coastal floodplains. My name's Duncan Rayner from the Water Research Laboratory at the University of New South Wales down in Sydney. And I'd just like to acknowledge my co-authors here, Alice Harrison, Toby Tucker, Prem Raman, Gabrielle Illuminati and Will Glamour. And so in New South Wales, there's a program called the Marine Estate Management Strategy, and that's a 10-year strategy focusing on the marine estate, so coastal waters, estuaries and biology and ecology and water quality within that environment. And it's a multi-agency approach between different government agencies, fisheries, Crown land, water, environment, different groups across different areas. And as a part of that strategy, as part of that initiative, there was a threat and risk assessment completed, so a TARA was completed. And that threat and risk assessment looked at all the things that might pose a major threat to the marine estate. And one of the key initiatives that came out of that threat assessment was that water quality is a big threat to the marine estate and to fisheries and to ecologies in the estuaries and coastal waters. One of the key initiatives was relating to improved management of diffuse water quality. So that's water quality that's not necessarily from point sources, but more diffuse across coastal floodplains in this instance, and across estuaries, and it's coming from multiple different sources. And so this led to the Coastal Floodplain Prioritisation Study, which we undertook. And now, in terms of this water quality, it's less so about nutrients and suspended sediments, which was looked at through other initiatives as part of the Marine Estate Management Strategy. And primarily we were looking at discharges and pollution from Azo Sulfite soils, low oxygen Blackwater, sea level rise, vulnerability of coastal floodplains. And so the Coastal Floodplain Prioritisation Study was really about focusing on poor water quality from those two sources, acid sulfate soils and low oxygen Blackwater, and identifying and prioritising the risks from those sources to the marine estate and figuring out where the high priority and the low priority areas were to really enable targeted management, targeted restoration. And so we did this using a multi-criteria approach to objectively rank sources of poor water quality from acid sulfate soils and from Blackwater, and then look at how coastal floodplains and estuaries might be changing under sea level rise and how floodplain drainage might be vulnerable, and really use a data-driven evidence-based approach, which also allowed a range of other constraints to be considered, environmental, social, economic and cultural floodplain values as well. And so coastal floodplains in New South Wales particularly have changed a lot over the last 100, 150 years. So prior to about 1950, there was a lot of ad hoc coastal floodplain drainage that was put in. And then a lot of that was formalised 50s and 60s in the construction of state-sponsored flood mitigation programs, which serve two purposes for flood mitigation, but as well as for drainage of coastal floodplains to enable improved agriculture. So here we see a site on the Macleay River floodplain on the mid-north coast of New South Wales near Kempsey. And here you can see where major flood mitigation works was installed, constructed, huge channels dug, major changes to the hydrology of coastal floodplains, literally blasting and dynamiting rock out of the way to enable more efficient drainage of coastal back swamps and coastal wetlands. And so this is just ongoing over the past 100 and 150 years, a change in the hydrology of coastal floodplains for that flood mitigation purpose, but also as well just for better agriculture and better drainage and lower water tables. And so that made it efficiently drain one way, but it also made it more efficient connection with the estuary. And so infrastructure's put in, one-way floodgates are put in to stop the tide come back in and to enable a drawdown of the water table and a draining of the floodplain. And so there's drains everywhere on all major floodplains in New South Wales. Here we've got the Tweed River and the Macleay River, dense networks, thousands of kilometres of drains, all with this one-way floodgate infrastructure installed on the end. Here you can see the Manning River Valley on the mid-north coast. It's the same up and down the coast. And so what has that done? Well, the two issues I'm going to talk about today are Azo Sulfite soils and Blackwater. So Azo Sulfite soils are naturally occurring sediments that exist all up and down the coastal floodplains on the east coast of New South Wales. And it's a naturally occurring sediment which prior to drainage would have been underwater. It's a neutral pH. When significant floodplain drainage is put in and one-way floodgates are put in and the water table is drawn down, it enables that Azo Sulfite soil to be exposed to oxygen. And essentially that creates sulfuric acid and other metal byproducts such as high concentrations of aluminium and iron, and that all flows down into the estuary and into the receiving water. What the constructive floodplain drainage is, and what it does, is it enables a strong gradient from the floodplain and from the soil matrix into surface waters, really driving a positive gradient of acidic water out of these acidic soils into the surface water drains and then into the estuaries. And so when you get these episodic events following rainfall, you have large plumes of iron, aluminium, low pH water in the 2s and 3s pHs, high concentrations of iron here impacting fisheries and marine ecology and marine biota, deposition of these materials in surface waters and in drains, and large plumes of this material that can be discharged into the estuary. Here we see a place on the Manning River and mid-north coast, and you can see an acidic plume that's impacting directly onto oyster leases there at the bottom of the screen. You also have a degradation from this over drainage to historical wetland areas, so scalding where you've got acid sulfite soils at the surface, and a general degradation of those wetland values. Low oxygen Blackwater is after the floodplain's drained, you have an establishment of non-water tolerant vegetation there. It's still very low-lying land though, so when it's subject to inundation following a flood event, that non-water tolerant vegetation decays, consumes oxygen, and then is released into the estuary, often with a high chemical oxygen demand and a high biological oxygen demand, which then further strips oxygen from the estuary and from the receiving water. So what that results in is large periodic fish kill events following wet weather, particularly following prolonged periods of inundation in summer. So it's called Blackwater because it is black. So this is nothing new. It's been going on for 50 years, but there is a general trend in that this is the way it's always been, and that's the way it is, and so that's the way it is, and that's not how it should be. There's been these massive changes, in these huge impacts, and they need to be addressed. But not all areas contribute equally on these coastal floodplains to this risk. And so we looked at 7 floodplains from the Tweed River in the north down to the Shoalhaven in the south of New South Wales, Richmond River, Clarence River floodplain, Macleay, Hastings and Manning River floodplains. And so to figure out where we might prioritise, where the highest risks come from, we broke down each of the coastal floodplains below 5 metres above mean sea level, below 5 metres HD, based on topography, hydrology, drainage, what the catchment is behind this floodgate infrastructure, and the geomorphology of the floodplain as well. And so here you see the Richmond River floodplain with essentially split it up into these sub-catchment drainage areas. So that allows us to go in and look at each characteristic of each one of those sub-catchments in each one of the study floodplains and look at, all right, well, where is the highest risk of that acid coming from based on the data that's there and based on the characteristics of that sub-catchment. So we use this multi-criteria based priority assessment approach, and that's looking at how much water is coming through the catchment. So what the ability of that acidic soil is to be flushed into the estuary, how dense the drainage network is and how deep it is, what the infrastructure is doing at the estuary, at the tidal boundary of the subcatchment at the floodplain, how acidic that groundwater is, how fast it can move, so how easily can it be transported from the ground into the surface waters, how far is it from something that's a sensitive receiver, maybe an oyster lease, seagrasses, conservation wetlands, Ramsar wetlands, those sorts of things. And then what the estuary is doing, where it is in the estuary, how much the tide's going up and down, of course, taking into account the land use. And so here you see the 7 subcatchments. the 7 floodplains, and they're all broken down in between 11 and 15, and in the case of the shallow, 39 different drainage areas. And you can see that there's a disproportionate risk of acid contribution from the top priority subcatchments. So you've got the top 3, 4 or 5 subcatchments generally producing between 70 to 90% of the acid risk. That really lets you target where, if we're going to get the best bang for our buck, we're going to get the best outcomes from this, where should we really be focusing, and justify investment and equally non-investment in different parts of the floodplain moving forward to get the best outcomes for water quality and wetland habitats in coastal floodplains. Similarly with Blackwater, we've got all these different subcatchments across these different study floodplains. And how do we quantify what the risk might be from these different subcatchments for generating Blackwater? Well, that's about understanding how Blackwater is generated. And it's typically distilled down to a number of key factors, and that is the area that might be inundated, and that's related to where it is in the estuary, what the elevation of the land is, the shape of the subcatchment itself, and then also the land use and primarily what the vegetation type is. So how easily can vegetation that's sitting underwater for 1, 2, 3, 5 days, 2 weeks, how is that going to break down, and how fast is that going to consume oxygen? And then where it is in the estuary. If it's closer to the entrance, closer to the ocean, it's going to be more tidal. If it's further upstream, it's going to have more of a flood influence during those flood periods. So that water sits on the floodplain for a certain period of time. It's being held up by the river. And then once the river recedes, Blackwater's been generated and it gets discharged in the estuary. So there really is a critical time for this. It's not about the peakiness of the flood. It's about the duration and the depth that area of the floodplain and that land, that pasture grass, sugarcane, whatever it might be, is susceptible to being underwater. So it's about that critical duration in relation to the land use and the vegetation type. Where it sits in the estuary is critical. So we went around and we looked at all this information, looked at the LiDAR, looked at the land use, correlated vegetation type with land use, and come up with a risk for that, how easy it is, how most likely it is to consume oxygen, and then looked at all these different ranges of inundation durations, all these different ranges of inundation depth in each one of the subcatchments in every floodplain. And that allows us to come up with this map of what is the median, what's the average contributing area for Blackwater generation in each one of these subcatchments, and therefore what the risk is from Blackwater. And so that allows you to come up with this prioritization of these are the key areas where this risk is originating from. So in terms of the findings, Blackwater isn't as clear cut as acid, but there certainly are priority areas, top 3 out of 15 subcatchments that are contributing the majority, if not up to 80, 90, 95% of the Blackwater risk within that particular floodplain. Again, I'm highlighting that there is a disproportionate risk, or there are particular subcatchments, particular parts of these floodplains that are generating the most poor water quality. Often they're the same ones that are generating a lot of acid as well. So critically, we also looked at what is the vulnerability of the floodplain. We know that drainage is very important for both acid and Blackwater production, and how's that going to change into the future, and how might sea level rise impact drainage, and how might that impact land use and management and planning horizons into the future. So we calibrated numerical models of every estuary. Just let me go back for a second, of every estuary. And here we're not talking about inundation by salt water, so the sea level coming up and inundating by salt water. It's about the ability of the floodplain and the land to drain, and that ability of the land draining being limited because the estuary or the river is higher. So there's just less of a gradient for water to get away. So we looked at present day 2050, 2100 planning horizons. We looked at all the floodgate infrastructure on all the floodplains and also the land surface on all the topography. So here in the Tweed, there's going to be an increase of 90 structures that are going to be highly vulnerable to reduced drainage, and an increase of 370 hectares that are going to be unable to drain by gravity. So they're essentially going to be below the future low tide level. In other catchments, such as the Clarence, that's up to 8,000 hectares. So large areas of land, they're going to be poorly drained. They're currently being used for agriculture. How are we going to manage that into the future? And so the outcomes for this were really identifying priority areas for restoration. Where is all that poor water quality coming from? So we can really target that management, target remediation, target rehabilitation to get the best bang for buck, and to make sure that investment is actually generating an outcome that is going to have a positive impact on the marine estate and a measurable change in water quality. We've summarised, this is a short snippet, we've summarised a lot of information relating to the geography, the geometry of drainage, where acid is, where Blackwater is, what the land use is, what the land values are, who owns what, the tenure, all these sort of things which feed into restoration. In terms of the science might be clear and what can be done, but it's a lot harder to implement. There's a lot more moving pieces. So this is intended to be a high-level planning guidance document, guide investment and equally non-investment, collate all that data, and also provide those detailed subcatchment summaries. So you can go and look at a particular area of the floodplain and say, all right, this is where the acid is, this is the land use, this is who owns what, how should we go about this? Also includes all those constraints about planning, environmental, sea level rise, what sort of trigger level are we going to have to enact change. The recommendations really focused on that catchment-wide approach, getting stakeholder consultation in early, having everyone involved, having the data on the table to enable those decisions to be made, and allowing some short-term and long-term options to be tabled from the beginning for consideration, but knowing that to get things designed well, we're going to have to go in at a subcatchment, those high priority areas, and really get into the detail before there's construction and on-ground actions done. Collate all this data in an estuary database and make sure that there's an ongoing commitment to monitoring and data collection. And so that's the Coastal Floodplain Prioritisation Study. Thanks for your time today.
Thanks, Duncan. Can you hear me on the microphone?
Yeah, sure can, thanks.
Yep. Okay, we've got a couple of minutes for questions, if anyone. Yep, Damien.
G'day, Duncan. Thanks for that. It was really good. Just wondering, when you talk about so those areas that are high priority, that are producing all the acid or whatever, in terms of restoring, are you talking about turning it from agricultural land like back into wetlands, or yeah, what would be the process for that?
So there's a range of engineering work. So there's a lot of work that goes on to remediate or to try and get environmental outcomes, environmental improvements, whilst maintaining the existing land use. So there's things that you can do depending on where you are. You can reshape drains so they're not as deep in the acid layer. You can manage how floodgate infrastructure works during dry times. Do you want to have some natural tidal buffering and some flushing and those sort of things? And so it really depends about how that land is managed. Where we've been involved in a lot of large-scale on-ground restoration works, where the best outcomes tend to occur from both a water quality perspective and a wetland habitat perspective. The most success generally occurs where there is a change in land use. There's a lot of mechanisms for that, but generally very low lying land is in many cases unproductive, subject to inundation, subject to reduced drainage. And so a change in land use from whatever it might be to conservation can really have the greatest outcomes. There are short-term options that allow the waterway to be managed, but they are somewhat of a band-aid.
Okay, thanks. And there's also a question online from Peter Dixon. How successful have the drainage decommissioning projects been to date in reducing acid in Blackwater and ecological improvement, for example, at Hunter River?
Yeah. So in the Hunter, for example, there's been, I'm just reading a question here again, Peter. So they have been successful in the Hunter. So there's a number of sites in the Hunter that we've been involved in. Tomago wetlands, for example, sites on Kooragang Island, there where there's been restoration of tidal flushing and tidal inundation, resulting in overland flow. And they're done for different purposes, some for water quality, some for habitat, but they are establishing intertidal wetlands if that's the goal, and attracting migratory waded birds from all over the world. So they are successful. It all depends on, like I said, that what the ownership is and what the intention is. Blackwater is a little bit more difficult because those drainage works that I showed at the start of the presentation, they changed the hydrology significantly. Historically, pre-European development, there would have been natural levees that are holding water back. So you would have had Blackwater events, but they're not as, the drainage works have increased the frequency and magnitude of those events. There's about a 90-day carbon cycle that occurs for that oxygen to that breakdown of Blackwater process to complete. And so Blackwater is a bit more problematic. You can have more water tolerant grasses, but you've still got this altered hydrology. So how do you deal with the hydrology is a bigger subcatchment wide issue.
Okay, thanks. There was also another question, but we've run out of time here. So maybe if you jump on the chat and respond to Marion.
Sure.
Okay, thanks, Duncan.
Thanks so much, everyone.